All right, welcome everybody. I wanted to make this video today to walk you guys through mass-to-mass problems in stoichiometry. Okay, so I realized that now our class time is a little bit more limited than before, so I want to save our actual Zoom class time for interactive activities, right? For interaction. So I'm hoping that if I do a video lecture like this, that you guys can watch it before class and we can get right into some more, interaction. All right. So let's get started. So what we're going to talk about is stoichiometry, and I'm just going to start today, kind of review the things that we've talked about and kind of start from the beginning. Right. I'm going to start from the beginning and try to walk you through everything here, okay? So with stoichiometry, what we're really studying is chemical reactions. And stoichiometry is basically a method for determining the amount of product produced or reactant consumed using a balanced chemical equation. So for most of the examples today, I'm going to work with this equation. So H2O makes hydrogen plus oxygen. And to balance the equation, we need two waters to balance the oxygens, and then two hydrogens, right? So stoichiometry in this case would be questions like how much water is needed to produce a certain amount of hydrogen, or how much oxygen is produced from a certain amount of water, or even how much oxygen is produced when a certain amount of hydrogen is produced. Okay, and so there are many different types of stoichiometry questions you can ask, and it really comes down to the units for the amounts, right? So how are you expressing the amount of each of these things, right? We've got several options. We can express the amount of something in moles. We can express the mass, the volume, or even the number of molecules or particles. Okay? So for today, and so far in the course, we've really only looked at moles and mass. Okay? All right, let's see. So how do you solve a stoichiometry problem? So solving stoichiometry problems. In general, there's two keys. One, you've got to be able to do unit conversions, right? And two, you've got to plan. You've got to plan how you're going to get from whatever information is given to you, and how you're going to get from there to the finish line, right? To the finish, to whatever they're asking for, right? So in terms of unit conversions, if we're working with moles and mass, you're going to need to be able to convert let's see. First thing you're gonna have to be able to do is convert between moles of something, right? Moles of A, and convert to the mass. And two, you're gonna have to be able to convert between moles of A and moles of B. Right? And by the way, you're going to have to be able to do both directions. So you're going to have to also be able to find moles of A from mass of A, right? And so to do these two types of unit conversions, you've got what you can call a toolbox. And in that toolbox, you've got two pieces of information that you're going to be able to use. For every substance, you can calculate a molar mass, right? And then for every chemical equation, you've got coefficients. Okay, so the molar mass you're going to use to convert between moles and mass, and the coefficients you're going to use to convert between moles and moles. And then lastly, plan in, right? So if we're working with a problem, we need to plan out how we're going to solve it first. Let's look at an example. Okay, so a mass. Actually, before we look at an example, let's talk about those unit conversions. All right, let's look at those unit conversions. Unit conversions. So the first one we're going to look at is going from moles of something to mass of the same substance. So for example, convert 1.2 moles of water to grams of water. Okay, so what we're going to do here is we're going to use the molar mass. So whenever you're converting between moles and mass, you use the molar mass. Right, which for water, H2O, so that's going to be two hydrogens. So you got two hydrogens. You're going to look up the molar mass of hydrogen in the periodic table. That's 1 gram per mole, approximately to the nearest whole number. And then you've got one oxygen. So you'll look up oxygen, that's 16 grams per mole. So the molar mass of water is 18 grams per mole. Okay? All right, now how do you use this information? So what this means is that 1 mole of water has a mass of 18 grams, right? So that's our key. That's our relationship. So what we're going to do is we're going to set up a conversion factor. So the molar mass is technically just a conversion factor, right? We can write two conversion factors with it. We can write 1 mole over 18 grams, or we can write 18 grams divided by 1 mole. Okay, so let's try to figure out which one of these conversion factors we need to use. We are starting off with 1.2 moles. And to do a unit conversion, you multiply by a conversion factor. And you want to end up with grams of water in this case. Oops. All right. So between these two options, I want to use 18 grams over 1 mole. And the reason is when I do this multiplication, I want the units of moles of water to cancel. So I need moles of water to be on the top over here and on the bottom over here, right? So I'm going to want to have mole of water on the bottom here. So it's going to be 18 grams over 1 mole, right? And then 1.2 times 18, real quick. Looks like it's 21.6 grams. All right. So that's converting from moles to mass. That's converted from moles to mass, right? You're going to use the molar mass. You're going to set up a conversion factor using that molar mass, right? And so when you set up your conversion factor, remember that the units that you're starting with go on the bottom, and the units that you're converting to that you want should be on the top of that conversion factor. All right, now let's look at the next type of unit conversion. So the next type of unit conversion that's important is converting moles to moles. So for this one, we need to look at the balanced chemical equation. All right, and so we're going to look at a mole to mole unit conversion. All right, so what we're going to do is we're going to convert, let's see, 3.6 moles of water. We're going to try to convert that to moles of O2. So in other words, we're trying to figure out how many moles of O2 are produced from 2 moles of water. I'm sorry, from 3.6 moles of water, right? We know that if I look at this equation, these coefficients, it's sort of like a recipe. It's telling me that 2 moles of water makes 2 moles of hydrogen and 1 mole of O2. Right? So it's like a recipe. 2 moles of water makes 2 moles of hydrogen plus 1 mole of O2. But we're not starting off with 2 moles, right? We're starting off with 3.6 moles. So that's going to be more, right? 2 moles of water would make 1 mole of oxygen, right? Just that's how you interpret the coefficients. Since we're starting off with 3.6 moles of water, we're going to have to scale this up, right? It's like taking a recipe and then increasing the amount of ingredients, right? That's going to increase your product too, right? So let's see. I can solve this problem a couple different ways. Let me show you the conversion factor way. So when I'm doing a mole to mole unit conversion, the conversion factor comes from the coefficients. The coefficients allow me to set up a ratio of one substance to another. Let me explain. I know that 2 moles of water is an equivalent amount as 1 mole of oxygen. So in other words, every time 2 moles of water react, 1 mole of oxygen is made. So I can set up a ratio between water and oxygen two different ways. I can write a conversion factor that is 1 mole O2 over 2 moles of water. Or I can write 2 moles of water over 1 mole O2, right? These are both ratios. In this case, it's water per oxygen. In this case, it's oxygen per water. They're just flipped, right? And so these ratios are conversion factors. So I can use one of these to convert from moles of water to moles of oxygen. So if I start off with 3.6 moles of water, I'm going to multiply by a conversion factor, and I want to end up with moles of O2. So that's the unit I want to end up with, which means that I want moles of water to cancel, to go away. So over here, moles of water is in the numerator, right? It's in the top. So I'm going to want to have moles of water in the bottom, right? That's what I'm going to want to have. So if I look at these two conversion factors, I'm going to use this one on the right here, right? The coefficient of water goes on the bottom. Coefficient of oxygen will then go on the top. Right, so then 3.6 times 1/2, well, that's going to give me the moles of O2 produced. So whenever you're doing a mole to mole conversion, you're always going to multiply. You're always going to multiply by a ratio of coefficients. The only trick is choosing which ratio to use, right? Because for any two compounds, I can write two different ratios because I can choose to have one on top or the other one on top. So you're going to choose the one that makes the units cancel, right? So you're always going to have the substance you're converting to on the top and the substance you're converting from on the bottom, right? And then you're just going to get those numbers from the balanced chemical equation. All right, so that's a mole to mole conversion. Now, there's one more type of conversion we should look at, and that's so unit conversion number 3. That's a mass of a particular substance converting to how to convert mass to moles. And this is going to be really similar to the moles to mass unit conversion we did at the beginning, but it's just the other direction, right? So in this case, we're going to use the molar mass, right? So for example, convert. Let's see. Let's pick 42. Convert 42.6. Kind of a random number there. 42.6 grams of water. Right? Convert that to moles of water. All right, so in the previous slide, we got the molar mass, right? We calculated the molar mass for water. So that's just using the formula for the compound for water, using the periodic table, looking up the molar masses, right? You're going to have 2 hydrogens, so 2 times 1 gram per mole, plus 1 oxygen, so 1 times 16 grams per mole. And so the total molar mass for water, 18 grams per mole, right? So 1 mole of water equals 18 grams, right? And so the 2 conversion factors I can write are 1 mole over 18 grams or 18 grams over 1 mole. So to solve this problem, let's see. We're starting off with 42.6 grams of water. We're going to multiply by a conversion factor. And we want to end up with moles of water, right? So I need grams of water to cancel, to go away. So I'm going to put grams on the bottom, right? So that means I'm going to choose this conversion factor, 1 mole over 18 grams. Right? So my answer is going to be 42.6 divided by 18, about 2.4. Now, we should ask ourselves, does this number make sense? You always want to, when you finish a problem, or even just finish a single unit conversion, you want to ask yourself, does your answer make sense? Let's think about it. If 1 mole has a mass of 18 grams, 42 grams, is that going to be bigger or smaller than 1 mole? Well, 42 grams is bigger than 18, so my answer better be bigger than 1 mole. And yes, my answer is bigger than 1 mole. 42, it's more than twice as big as 18, so my answer should be more than twice as big as 1 mole, and it is. It's bigger than 2. Makes sense. All right. Now let's try to put it all together, right? So let's put it all together. And so we're gonna look at mass to mass problems now, right? And so this is a problem where, one, you're given a balanced chemical equation, right? You're given the mass of a reactant or product, but you're just given one, right? You're just given one reactant or one product, and you're asked for the mass of a different reactant or product. Okay, so let's look at an example. Let's take our water split-in reaction. Right, and let's say how many grams of O2 can be produced from 50 grams of water, right? That's a typical mass-to-mass problem. You're given the mass of water, so grams, that's a unit of mass, and you're looking for grams of O2. So you're trying to convert from mass of water to mass of O2, right? So if you think back to the beginning of this, what are our two keys? Unit conversions, right? We're going to have to do unit conversions, but more importantly, we have to plan, right? We've got to plan how to do this because it's not going to be a single step. Let's look at it. So here's my plan, and the plan is going to look the same for any kind of mass-to-mass problem. So I'll just write this as a plan for mass-to-mass problems. We're given, we're given grams of, let me get this right. Yeah, grams of water. We're given grams of water. And we would like to end up with grams of O2, right? That's what we want. But there's this big space, there's this big gap between, right? How do we bridge the gap, right? Well, if we think back to the unit conversions we did, the only one that involves two different substances would be this mole to mole unit conversion, right? You can see here we converted moles of water to moles of O2. Now this was a different number probably than what we're dealing with here in our problem, but we know how to do this. We know how to go from moles of water to moles of O2. We're going to use one of these two conversion factors, right? So I can get moles of O2. I know how to do that from the moles of water, right? So that step is kind of in the middle here. Now, once we have moles of O2, we know how to get grams of O2, right? This step, this involves using the molar mass. This step involves using the coefficients from the reaction. And then finally, to get the ball rolling, we're going to start off by converting grams of water to moles of water, and that's using the molar mass as well. Okay? So let's take a look, right? Each of these steps we've already reviewed, right? We've reviewed how to do grams to moles for one substance. We reviewed how to do moles of one substance to moles of another. And we looked at how to do moles of a substance to grams of a substance, right? So let's take a look. Let's put it all together, right? If we have this plan, then it really just comes down to doing those unit conversions, which we should be comfortable with. Let's see. Let me rewrite the problem here. And I'm starting off with, what was it, 50? 50 grams of water. That's what I'm starting off with, right? And I want to know how many grams of O2 I have, right? So step one, let's number them, right? Step one, step two, step three. Step one, 50 grams of water. I need to convert, right? I need to multiply by a conversion factor. And for step one, I want to end up with moles of water. All right, and so let's try to figure out what the conversion factor should be. So for a mass to moles conversion, I'm going to use the molar mass. And so the molar mass for water, we showed earlier that it is 18 grams per mole, right? So I've got a couple different options. I can do 18 grams over 1 mole or 1 mole over 18 grams. So on the top and on the bottom here, I'm going to put 18 in 1, right? 18 grams in 1 mole. It's just a question of which one goes on the top, 18 grams or the 1 mole, right? Well, I'm converting 2 moles, and I want grams to cancel, so I'll put grams of water on the bottom and moles of water on the top, right? And so this molar mass tells me that 1 mole of water is 18 grams. So 50 grams to find the number of moles in 50 grams, that's going to be bigger than 1 mole, right? Because 1 mole is 18. So this is going to be considerably bigger because it's considerably bigger than 18, right? To get the exact number, I'm going to do 50 times 1 over 18. 2.8, or let me do 2 decimal places. 2.78. 2.78 moles of water, right? That's step 1. We found the moles of water. Okay. Step 2. Step 2. You've got 2.78 moles of water, and you want to multiply by a conversion factor, right? And you want to end up with moles of O2. And so I'm going to put that reaction here at the top. All right, so we're going to use the coefficients. Now, the 2 substances, water and oxygen. The coefficient for water is 2. Coefficient for oxygen is 1. So my two conversion factors would be 1 mole of O2 over 2 moles of water, right? 2 moles of water produces 1 mole of oxygen. Or 2 moles of water over 1 mole of O2, right? I can flip it too. So it's either 1 mole of oxygen over 2 moles of water, or 2 moles of water over 1 mole of oxygen. And that's because 2 moles of water, this is equivalent to 1 mole of oxygen, right? 2 moles of water consumed is equivalent, is going to lead to 1 mole of O2 produced. All right, so to figure out which conversion factor I want to use, I need to recognize which unit I want to cancel. I want to end up with moles of O2, so I want moles of water to cancel. And moles of water is in the top here, so I'm going to need to put moles of water in the bottom, right? So that means I'm using this conversion factor. The coefficient for water goes on the bottom, coefficient for oxygen goes on the top. 1 mole of O2 is the same as 2 moles of water. Okay? So the number of moles of oxygen I make is going to be 2.78 times 1 over 2. So 1.39 moles of oxygen. Now, we should ask ourselves, does this make sense? Does this make sense? Well, we know that 2 moles of water, following the recipe, right? This is a recipe. 2 moles of water makes 1 mole of O2. But we don't have 2. We've got 2.78, right? So that's a little bit more than 2. So we're going to make a little bit more than 1 mole. And our answer is a little bit more than 1 mole. So that seems to make sense. And the amount of oxygen we make is half the amount of water we started with, right? And so that makes sense if you look at the ratio as 2 to 1. All right, let's finish the problem. Step 3. Step 3. The question asked how many grams of oxygen are made, right? It didn't ask for the moles of oxygen. It asked for the grams of oxygen. So we're going to take 1.39 moles of oxygen, and we need to convert it, right? We need to convert it. And so we need to end up with grams of oxygen, right? And so in this case, we're doing a moles to grams conversion, right? So we're going to need the molar mass for oxygen, for O2, right? So there's 2 oxygen atoms, so that's going to be 2 times 16 grams per mole, or to the nearest whole number, 32 grams per mole. So again, we've got 2 types of conversion factors we can write. We know that 1 mole of O2 has a mass of, oops, I wanted to say 18 again, but that's for water, of 32 grams. So I can write 2 different unit conversions. I'm sorry, 2 different conversion factors. I can say 32 grams is 1 mole, or I can say 1 mole is 32 grams, right? These are equivalent statements. Now, which one of these is going to get me my right answer over here, right? So I'm going to take my 1.39 moles and multiply by the conversion factor that will allow me to cancel the units and get grams of O2. So moles of O2 has to be on the bottom so that the units will cancel. So I'm going to need to use this one, right, that has moles on the bottom. So 1 mole O2 is 32 grams of O2. Okay? And so 32 times 1.39, that's 44, and I'll round a little bit here, 44.5. That's going to be my final answer, right? So if I start off with 50 grams of water, I end up with 44.5 grams of O2. So let's just double check and make sure things make sense. I had 1.39 moles. I know that 1 mole is 32 grams. 1.39 is bigger, right? 1.39 is bigger than 1 mole. So my answer should be bigger than 32, which it is. Makes sense. Now, does this also make sense from the context of the reaction, right? Does it make sense that does it make sense that does it make sense that 50 grams of water makes 44.5 grams of O2? Is it at least possible? Is it plausible? Right? Is it possible? Well, what do we know about chemical reactions? We know that during a chemical reaction, atoms are neither created nor destroyed, right? So we're just rearranging the atoms, which means that the total mass has to stay the same, which means that we have to have conservation of mass, right? So mass can neither be created nor destroyed. Well, what does this mean? This means that the mass of O2, is there a limit on what it could be? Well, we start off with 50 grams of water. 50 grams of water. So the total mass of whatever the products are, that total mass can't be larger than 50. My mass of my oxygen has to be less than 50 grams. And I say less than and not less than or equal to, because I know that there also has to be hydrogen. there also has to be hydrogen, right? The reaction doesn't happen. Oxygen doesn't get made in isolation, right? So is my answer of 44.5 grams plausible? Well, it doesn't violate conservation of mass, right? It's less than 50. All right, let's look at one more example, and so I just walked you through a mass-to-mass problem in a lot of detail, right? A lot of detail. Let me sort of summarize this method with another example, and we'll try to go a little bit quicker, all right? Let's take the same equation. And now let's ask a different question. What mass of water is needed to produce 100 grams of H2? All right? So this is a pretty interesting question because this reaction, you're splitting water to make hydrogen and oxygen. This reaction is not spontaneous. We'll get into that later in the year, but it's not spontaneous. I'll just put it up here. For now, all that really means is that this reaction, it doesn't just happen. It doesn't just happen. It takes energy to do this, right? There's a penalty. You've got to pay an energetic penalty to get this reaction to occur, right? And you guys kind of know this because if you have a glass of water, it doesn't just break apart into hydrogen and oxygen in front of you, right? You really need to do something to it. You really need to do something to the water to cause this reaction to happen. You really got to do something, right? And so this is something that a lot of people in the energy business, right? A lot of people in the energy industry are very interested in because of H2, And so H2 is very interesting because it's a very promising fuel because when you burn hydrogen, burn in hydrogen makes only water. Burn in hydrogen makes only water, right? So if you can get energy from burning H2 instead of something that has carbon in it, well, you're not going to have the same carbon dioxide emissions, right? And so you're going to emit, less greenhouse gas. H2 is the ultimate clean energy source, right? It's the ultimate clean energy source because your waste product is as benign as it gets, right? This is as harmless as it will ever get, right? Water is the ideal waste product, right? So a lot of people want to get hydrogen. A lot of people want to burn hydrogen. Well, the problem is that where do you get it, right? Where do you get it? Oil you can dig up in the ground, right? Coal, you can mine coal, right? Natural gas, these are all things that you can sort of just dig up, right? There's natural supply of this stuff. But the H2, the hydrogen, it's pretty much stuck in water for the most part, right? We've got a lot of water on Earth, but if we're going to get pure hydrogen, we need to be able to split water, right? And that takes energy. All right, I digress. That was a little bit of a detour there, but that's why this is really interesting. Like, it's important to be able to know how much water would you need to make a certain amount of H2, right? Because we really do want to make H2 from water. So let's set this up. All right, we're starting off, right? We're starting off with the mass of H2. We want to end up with mass of water, which means that we're going to find moles of water from moles of H2. And so we've got the same steps as before, right? Step 1, step 2, step 3. Step 1 is a mass to moles conversion, right? So we're going to need the molar mass. So let's write that over here, molar mass. So for H2, that's 2 hydrogens, right? So it's 2 times 1 gram per mole. That's 2 grams per mole. For water, we found that earlier, that's 18 grams per mole. Okay, so the first step, and I promised we'd go a little bit quicker, so that's what I'm gonna do. 100 grams of hydrogen. How many moles of H2 is that, right? We're gonna multiply by a conversion factor, and we need to end up with moles of H2. So that means we need grams of H2 to cancel. So that has to be on the bottom. We need to have moles of H2 on the top, right? And I know that one mole of H2, that equals 2 grams. 1 mole of H2 is 2 grams. That's what the molar mass tells me, right? Molar mass is 2 grams per mole. So in this case, I'm going to put 1 mole on top and 2 grams on the bottom. So the moles of H2 is going to be 100 grams times 1/2. That's 50 moles. All right, let's look at the next step. Step 2. That's converting moles of H2 to moles of water, right? So we've got 50, not grams anymore, 50 moles of H2. We want to multiply by a conversion factor, and we want to end up with moles of water. Okay, so if I look at my balanced chemical equation, I know that 2 moles of water produces 2 moles of H2, right? So they're equivalent. They're equivalent amounts. 2 moles of water makes 2 moles of H2. But we're not talking about 2 moles. We're talking about having 50 moles, right? 50 moles of H2. How many moles of water would that be? Well, you just have to look at what is the ratio between water and H2, right? The ratio between water and H2 is this conversion factor. I want H2 to cancel. I want to end up with water. So I'm going to put moles of H2 on the bottom, moles of water on the top. And I know that 2 moles of water is the same as 2 moles of H2. So my moles of water is going to be 50 moles times 2 over 2. Well, 2 over 2 is just 1, right? So I'm going to end up with 50 moles of water, right? That makes sense because they're equal, right? There's an equal ratio. For every 2 moles of water, you get 2 moles of H2. So for every 1 mole of water, you would get 1 mole of H2. So for 50 moles, you get 50 moles. Okay. Finally, step 3. Now you're going from moles of water to the mass of water, right? And so we've got 50 moles of H2O. We're going to multiply by a conversion factor, and we want to end up with grams of water. Okay. Molar mass, right? What's in our toolkit? In our toolkit, we've got molar mass and coefficients for now, right? So the molar mass is what we're going to use to convert between moles and mass for a single substance. So the molar mass for water, 2 hydrogens plus 1 oxygen, that's 18 grams per mole, right? Which means that 1 mole of water, this equals 18 grams of water. 18 grams is 1 mole, right? But we don't have 1 mole. Instead, we've got 50 moles, right? So we're going to write a conversion factor. We can write 1 mole is 18 grams, or we can write 18 grams is 1 mole. So it's just a matter of deciding which one of these goes here, right? Well, we want to end up with grams. We want to get rid of moles, right? So moles have to cancel. So I'm going to need to have moles on the bottom, right? Moles of water on the bottom, and then grams of water on the top, right? So I'm going to use this conversion factor, 18 grams over 1 mole. All right, so that's going to be 50 times 18. That's 900 grams. So if I go back to the original question, we've got this balanced chemical equation. And now I know that 900 grams of water are needed to get, now what was the original amount? 100 grams of H2. And since if all 900 grams are consumed, that means they're gone now, right? If they're all consumed, they're gone. So we should still have 900 grams of something, right? So if we get 100 grams of H2, that also means we'll have 800 grams of O2. So that's mass to mass problems, all right? So I'm hoping this video helped you guys out a little bit. You know, it's recorded, so you guys can rewind, go over just smaller sections at a time. But to summarize, I just want to summarize what we did today. So, summary. So we went over unit conversions, right? We went over unit conversions. And we looked at 3 different unit conversions. We looked at converting moles of a substance to mass of a substance, right? In which case you use the molar mass and you set up a conversion factor. So let's say we had 2 moles of water. You would multiply by a conversion factor that contains the molar mass, right? The molar mass for water is 18 grams per mole. So in this case, you need to have 18 grams on the top and 1 mole on the bottom so that the moles will cancel, all right? And then you would end up getting your number 2 times 18, 36 grams of water. We then looked at converting moles of one substance to moles of another, right? So that's a mole to mole problem, right? And so you're gonna end up taking the moles of one substance. So let's say moles of water and multiply by a ratio of the coefficients. So the coefficients go here. And let's say you're trying to get moles of H2, then the coefficient of H2 should be on the top, and the coefficient of water, which is what you're starting with, goes on the bottom. Right? And then we looked at converting mass to moles. Right? So this is the opposite of one, right? This is the opposite of the first unit conversion. You're going to take, let's say it's 50 grams of water. You're going to multiply by a conversion factor. In this case, you need to have moles on the top and grams on the bottom. So the conversion factor is flipped, right? It's 1/18 instead of 18/1. And so this is going to give you moles. Okay, and then the last thing we looked at was mass to mass problems, right? So we looked at, if you have a chemical reaction and you're trying to get from mass of one substance to mass of another substance, right? Maybe it's this reactant and this product, then it's going to be a 3-step process. You're going to convert the mass to moles. Then you're going to convert moles to moles. And then finally, moles to mass, right? So if you follow this plan, if you think about where you're starting and where you want to end up, and you look at how to get there, then the problem really comes down to doing 3 unit conversions, right? So you should be comfortable with those unit conversions. Comfortable, so you need to know how to use the molar mass, and you need to know how to use the coefficients. Okay, and so these coefficients allow you to set up what's called a molar ratio, right? The ratio of moles of one substance to moles of another based on that balanced chemical reaction. All right, that's it for today. Thanks for watching. Have a great weekend.